So this is the whole building model we had toward the end of the last tutorial before I extracted a floor. Now I'm going to repeat that process, but there's a few things I want to do to the model just to make it easier for us when we come to do the analysis and the interpretation of one floor. So the first thing I'm going to do is, you see at the bottom, that's the kind of grid that we defined, but it's only on this z equals a 0 axis. But we want it really to be at the floor that we're extracting, which, as before, we're going to extract these at fourth floor. So knowing that each floor-to-floor height is 3 meters, we want to then adjust that so we can also see it at 3 meters at 12 meters height, so the fourth floor level. So I'm going to come over to geometry and look at grid planes. So here essentially it allows us, amongst other things, to control kind of where these grids are shown. So I'm just simply going to say fourth floor, return it a few times, and then we know it's at 12 meters high, and that's it. So if we now come out of that, so nothing's changed yet, but if we come down to this bit in the kind of bottom right of the screen, we should, if we go to global grid, to the first box, we see 4 floors now appeared in the options. If we click on that, you see the grid is now jump up to the 4th floor. And again, as before, pressing the sort of grid button at the top menu bar kind of toggles off the grid as a whole, just shows the grid lines, and shows the grid lines, shows the plane, and then the grid lines with the with the plane itself. So that just again is going to be a convenient reference for me when I'm working with the actual floor model itself. So the next thing I want to do is to add in a edge beam. So just to make it sort of easier for myself, you remember we defined the 4th floor before as a list of elements, so that's my sort of 4th floor now. Just because it's the way I work, I'm just going to delete all of the elements that were created for the analysis before. So again, if we press Control Alt and D, there's nothing at all in the analysis layer. And of course, by getting rid of those, I've lost my my view here of the fourth floor element. Excuse me. So if we look at the slabs, using the volume tool, 1, 2, 3, the 4th floor again, it's got the grid along it or on it. So that's the sort of 4th floor. So again, I'm going through this pretty quickly. It's basically stuff I've covered in the last video. But what I want to do now is to add in a beam, say along one edge here. So this is just for purposes of examples a bit later in the tutorial. So we can go to the sculpt menu, which is here, or the sort of menu here, but I'm going to go to the sculpt menu. We've got the add entities tool, so we want to add in essentially a beam. So if I click on that, it's given me the sort of options here to set the kind of properties, the restraints, the releases, etc., etc. So what I want to do is quite simply, if I put on the nodes just to make it clearer, we've got nodes here and here. I'll number them just because, again, we're looking at the members. So I'm going to click there and click there, and that gives me a beam going along the edge there. If I shrink, you can kind of see it there. So because we've only got one beam property defined, which is the circular columns, that's why that's shown as a circle. Obviously, we can do this in a range of ways, but I'm just simply now going to go into properties, go into section library, and I'll define a beam. So again, using the wizard. So let's say it's 500 deep by, say, 250 wide. RC beam. Again, we want it's a concrete section. So 500 by 200. So that's putting in the section size, finish, and that's really it. So we're not offsetting it or anything at this stage. If we click OK, so it's property 2, you see at the side. So coming back to the design layer, again the kind of pink background tells us we're in the design layer. This is the beam that we just defined. If I choose the Select Elements Members tool there, if I select that, just because it's a selection that's both covering the beam there and the 2D member, it asks me what do I want to select. So you can cycle through it. By pressing next, you can see that highlights the whole member itself, the 2D member. Next again is the beam that we want. So that's what we want to select, so click OK. And what I want to do now is coming over to the right hand side, you can see the beam section I've added to the properties, and I'm going to then select that, and we see it changing there in the design layer. Again, we're working in the design layer at the moment, so we need to convert these all eventually into the analysis layer. So that's fantastic. That gives us a beam along the edge. The other thing that I want to do before I create the mesh, which is one of the reasons I deleted it all, was I want to give each of the panels their own sort of property or their own group definition. And in that way, it allows me to look at patch loading. So if we come to general data in the gateway column on the left-hand side and lists. So you see we've used groups 1, 2, and 3 already. So I simply want now to define a number of new groups. So firstly, I'll start by selecting. If I turn the view, and I should have said, although I've got the member tool selected here, if I hold down Shift and my middle mouse button, it allows me to rotate. So I don't need to go to the rotate tool explicitly. So I want to select these at first, slab, a member there. And I'm going to call that, so I'm going to come over then to the right hand side and change the group number to 11. If I hit return, that's then assigned that. Of course, the reason it's disappeared is because if we come back to our lists, you see slab is defined as only being a group 1. And that's what we're displaying there. But because we've just changed that to group 11, then that's why it's disappeared from this particular view. So if I go on to choose this slab, I'm going to call that group 12. Simply calling that 13. 14. 15. And 16. So I'll just now come back to my lists, and I'll say call one maybe 4th floor slab. Again, I'll say these are members, and I can simply type in G11 to, I think it was G16, and that essentially covers all of the groups from 11 to 16. Yes, I could have typed in G11, G12, G13, but that's a shorthand way of doing it. Just as before, I'm going to also define a list explicitly for the elements which will be created. And again, here, if I press equals, it copies what I've written above. So all fairly straightforward so far. So now, if I come to here, if I click on 4th floor slab, we can see the slab itself. And again, this is something I'll use a bit later, principally when I look at patch loading. So if I now come back to all, we're now back with our building. I'll take off the shrink, I'll take off all of the annotation, just to make it easier to see. So that's really it. I will now save just in case. So as before, if we go to Model, Coordination Tools, and Create Elements from Members, that then converts all of the design layer essentially into something that we can analyze. So I've already done that just to save time. If I switch to the design layer, we can see our model. If I turn on the sort of the shading, we can then kind of see on the perimeter the beam we've added there. Obviously, we're seeing the whole model here. If I go to my 4th floor itself, so that's of course only showing the slab. It's not showing the edge beam. You remember before we can type in P for property, B for beam elements. We know the slab, so we know the beam is property 2. If I press return, we can now see the beams appeared. And as I said, if we look at edge on, you see the beam itself is centered in the plane of the slab. So that's essentially it. Those are the changes I wanted to make. I'll take off that. I will go back to my kind of full view. So that's essentially it. I'll save again. And now it's as before. We go to Model, Coordination Tools. We want to extract a submodel. So let's call it the 4th. Well, we're extracting the 4th floor. So the thing that I've forgotten to do, which I'll return to in a second, is obviously kind of here I haven't updated the list to cover the changes I've made. So if I cancel out of this and then return to the model. So this is the floor that we want to extract. If I look at this, so the members only showing the actual slab itself. If we go to Elements, 4th floor, we can see everything there. The thing which is missing, of course, is the edge beam. So if I come down to Lists, 4th floor is here, and I simply then want to maybe add in to the end of this PB2. So you see I can have the element numbers, but also the property type as well. If I now come out of that, we should see the beam along the edge, as you see there. So that's then the 4th floor. I'll save this again. So again, let's now come into Model, Extract Submodel, and the same as before. So I'm going to go through this, extract a model, and then restart up the individual model of the floor itself in a few seconds. So I've extracted the floor. I've given it a new name, 003-2. Again, I'll make these files available. And if I click Open, that should then take me to my submodel. So that's the model. Loading again looks okay. So you remember in the last video it didn't seem to extract correctly. I'm not sure what was happening, but here it does seem to have worked. There's no kind of settlements as we saw before, so everything here seems okay. If I quickly check the restraints, so again it's all fixed, and again as before I want to take off the Z fixity, the vertical restraint at the top. So again, if I choose the nodes or the node selection tool, I'll highlight the nodes to make it easier for me to see. I'll select all this and then release Z. So these are the releases that you see there. I've unticked Z, so it's now free at the top, and you can see the letters have changed as well. So that's all fine. So I've gone through this all quite quickly, basically because it's a repeat of what we covered in the last tutorial video. You see also that my kind of 4-floor grid is also showing, so that's what I wanted to see. If I take off shrink, if I go to the labels and display methods option, to display methods, and if I go by group and hit apply, so you can see, if I maybe put back on the shading, that each of the colors shows that each of these panels is a different group. And as I said, I'm going to use that when I apply or put on additional load cases to look at patch loading. So get rid of that, just because it's maybe easier to work with without all the kind of colors. Again, I'll come back to the edge beam itself a bit later. So let's look at the actual loading. As I said, I defined the patch loading, or I defined the groups to give the different panels a different reference, so I can apply patches of load. So let's just look at that to start with. So my load case specification is got self-weight, the superimposed dead load, and the live load. So of course, because the self-weight and the superimposed dead load all come from the same condition, there's no need to patch those. But the live load isn't the same, so we're going to apply live load patches. So if I think of doing live load, I want essentially strips in X and Y that alternate, so there's no need for a checkerboard type pattern. So I'm going to say live load in the X direction, and call it strip 1. And then I'm going to say live load in the X direction, strip 2. And maybe just so it's perhaps easier or to relate this to the model, if I turn off the various toolbars just to make the screen a bit bigger, if I press the view tool to view it from the top. So we've got essentially a strip going in this direction, another strip here. So again, looking at this at column grids, and then I've got 1 strip, 2, and 3 strips in the Y direction. So I'll do exactly the same thing for Y. So you see there, I've given strip 1 and strip 3 exactly the same reference, because they will essentially be a patch that happens at the same time. So we'll have full loading on this strip in the Y direction, full loading in this strip in the Y direction, and no live load in this strip here. So that then gives us the cases that we're going to use. Obviously, if we said our combination is case 4, so the case here, number 4, and case 5, that obviously gives us live load everywhere. So again, holding Control and pressing the number pad on my keyboard, that then moves the various windows about. I'll come back to so I could open the gateway again by pressing the toggle button there, but this time just to show it a different way of getting to the same place. If I go to Model, Data Modules, and this essentially is all the same entries that you see when the gateway opens on the left-hand side. So I want loading. So load case specification is what we've got on the top right of the screen. So what I want to do is I've got my face loads, so that the 2D, the loading on the 2D elements. And again, I'll move that to there. So that's essentially the list we've got, or the items we've got listed already. So I could obviously select a range of elements and paste them in here, but that really isn't very good. I don't like that just because it's not very clear what it is that they actually apply to. So really in here I want to actually have a list rather than the numbers that you see there. So going back to here, so lists are in general data, so lists. And simply what I want to do is maybe just copy from my load specification these names into the lists. So if we remember, in the X direction, we had the odd group numbers in the first X strip and the even group numbers in the second. So I'll do G11, G13, and G15. So it's because I hadn't changed the type. It's giving me the error. Again, out of interest, it's interesting. What's useful that this has come up. Again, it gives you a bit of a help with the syntax. So if you get it wrong and you get this error message, usually it is quite helpful. If I actually cancel that, which is a bit annoying. But if I go to element, or change it to element, G11, G13, and G15, this time it works perfectly. I could have done G11 to, I think G15 to G11 step 2 or something. Again, I've done exactly the same thing again. Change that to element first of all. Again, there's various ways of doing lists. You could do G11 to G15 step 2, and that will give you exactly the same thing. Essentially, it's telling the software to go between group 11 to group 15 and to add 2 each time. But I'll keep it simple. G12, G14, and group 16. So those are the two X groups. So it's a bit more. So it's exactly the same process for the next two strips. So I'll just pause the video and fill these in and start again. So I've now completed the list of the strips, so you can see that there. So how do I check that this is what I want actually to see? So I go back to my view, selecting elements. We now see that these have all appeared in the drop-down list. So quite simply, I can now just kind of cycle through the list and just check visually that it is what I want. So that's my first X strip, that's my second X strip, that's the first and third Y strips, and that's obviously the middle Y strip. So it's given me exactly what I was expecting. So the whole point, of course, of doing this, as I said, was to be able to use just minimize that. The whole point of doing this was to be able to use it within the actual loading dialog. So you can see now the 2D element list essentially shows the strips, or the list of strips, which makes it much easier to define the loading. So I'll just select each of these. Oops. Strip 2. And then I want to then change this. Again, in the drop down, it's the names we've given in the load specification. So that's 4, 5, 6, 7. So these numbers obviously correspond to the case that you see here in the load specification. And in each case, it's all minus 1.5. If I press equals and press down, it just copies what was above. Now you see I've also got this live load case here, which essentially selects sort of all of the elements. Now that's fine. You can have duplicates ways of applying load, but because really each of these are individual cases, and it's when we come to do the combinations that we then look to combine these. So if I just close this, we don't need, oh no, we'll keep up the load specification just so we can see the names, and then go back to model, data modules, and tasks and cases, and we want combination cases. So these are the cases we defined before. We've got the SLS case and the ULS case. But we want to maybe look at patch loading. So what I'm going to do is I'm going to type in the various combinations whilst I pause the video and then come back and explain what I've done. So there are a whole host of ways to define how the loads actually appear, how you define the various combinations. So this is simply the way that I've chosen to do it. It's the way I'm familiar with. Obviously, you could find a way that suits you better, but the principles I'm going to explain are broadly the same. So you see I've added in combination cases. So within the combination cases dialog, I've added in combination cases 3 to 8. And combination cases, as the name suggests, is just combining a set of analysis cases, or indeed other combination cases, as we'll see. So for simplicity, I've added in my first combination case as the ultimate dead load. So that's simply A1 plus A2, which, as we see from the load case specification, I've defined as my self-weight and my superimposed dead load. So taken together, these are my dead load, and I've got the 1.35 factor applied to that. So that's the ultimate limit state, the factor dead load. But obviously there's the imposed load as well. So I've got my patch loading. So essentially each of the strips I'm considering as a patch which coincide with the dead load. So the reason for defining case 3 is then when I look at each of the individual combination cases, each of the patch loading cases, I can simply type in C3, so combination 3, plus 1.5, the load factor, times the analysis case of the live load strip. So A4, if we look at element loading here, A4 is the strip 2 in X. Sorry, A4 is the live load is the live load X strip, the first one. Getting myself confused. I should really be looking at load case specification. A4 is the fourth case, is the first strip in X. A5 is the second strip in X, and so on. In a way, the thing to remember to check, and it's an easy mistake to make, I've made it myself, is don't confuse the record number with the case number. They're two very different things. So when you're looking at the element loading, it's really the load case number here that corresponds to load case specification, which is what we put into the description of the combination case itself. So I've got these are my 4 patch loading combinations. But then to compare them all to essentially find the worst value, this critical case, you don't need to compare each of them individually. You can create an envelope case, and to do that, again, these are names I've just used for what I'm familiar with, but I've got my ULS, it's an envelope, and to create an envelope, you simply type C4 to C7, or you could do A1 to A7 if you were looking at just analysis cases, and that's going to take the worst values that you get from the combination cases that you've got here. The thing I realize I've missed is the case where we've got the live load on all of the slab. So I want to paste that down to there just to move it about. So ULS and the live load on all bays. So C3 is the combination 3, which is the ultimate dead load case, plus 1.5 as the factor. Then in brackets, I'll put A4. So A4 plus A5. So we remember that A4, if I look at my load case specification, is the first X strip. A5 is the second X strip. So together, then that's applied the live load to all of the slab. And that's it. So that's all of our combination cases applied. And we've got an SLS case from before, which is just the full SLS load applied on all slabs. Again, the principles are exactly the same. So if I get rid of the dialog, maybe we want to actually check that the loads be being applied correctly. So if we've got our graphic view selected, we can come over to the contouring, we can look at loading, 2D element loading, and look at face pressures. Again, there's a whole host of options. I'm going to contour them based on the actual value, and if I choose apply, and OK. So nothing's happened because we've not chosen an analysis case. But let's look at the ultimate limit state case. So this is what we looked at before, or defined in the last session. Not totally sure why there isn't anything appearing there. I'll just pause this a second and figure out what's happening. Yes. Again, the wonders of doing this live gives me a bit of pause at times to understand why things are appearing as they are. So the reason there's nothing appearing on the screen is that I've chosen to display a combination case. Now, combination cases are only processed after the analysis is complete. It's a post-processing operation, which is why we're not seeing anything reported here. If I come back to the base cases, the analysis cases, so self-weight, again, these are the input to the analysis. So these happen or exist before the analysis is carried out. So that's my self-weight, as I'm expecting. The slab's the same thickness, so I'm expecting to see the same loading. That's, as I said before, is based on the self-weight. And if I just toggle through these, so the superimposed dead load, again, it's the same on all panels. If I go to my case 4, my first X strip, so you see we've got loading on that strip and nothing at all there. If we wanted to check, we could zoom in, we could choose the annotation tool, select a patch of elements, and you can see we've got 1.5 in the red zone and 0 in the blue. So that's what we're expecting. If I go to the second X strip, again, that is reversed. The first Y patch, so we've got loading on this strip, loading there and nothing there. So that's what we expect. And then it reverses. So on the whole, it's exactly what we expect. It's showing that I've got my loading applied correctly. And again, doing these visual checks is one of the kind of key things to do. That's very straightforward, very quick to do, but helps us to make sure we've got the load applied to our model. So the thing I noticed I skipped over a bit quickly is my load case 2 and 1. Well, one's there because that's the self-weight, sorry. Load case 2 and load case 3, which were the initial loads I defined before starting this analysis. There isn't anything showing on the screen. And if we come to the element loading where it's defined, we see case 2 and case 3 have been defined by the element numbers. So one of the issues with the design layer is if you delete the elements and then recreate them, there's no guarantee that, well, it's almost certainly not going to give you the same element numbers applied to the same areas, which is why it's good to use names here as opposed to element numbers. So this list of numbers, of element numbers, don't actually exist in this model because we've extracted it. So that's kind of why there's nothing being seen here in terms of the load applied to the slab. So to correct that, we want to choose essentially a list of elements that we know will exist, but we want to avoid using element numbers. So I'm simply, because I know that the superimposed dead load is applied everywhere, I'm going to well, there's a range of ways that I could do it. I'm going to maybe choose the list for the two strips. So I know that the X strip 1 and X strip 2 covers the entire slab. So I can, again, cut and paste. And that's turned white just because it's trying to refresh itself. If I come over to the right-hand side, I choose the rescale option. Now it shows the actual values that we've applied. If we come back to the superimposed dead load, that rescale again shows everything's at 2, which if we close down the toolbar, we can see we've got a dead load, a superimposed dead load of 2 kPa on the slab. So that's what we expect. But again, it's one of the things to watch out for. Again, it's checking visually if what you see is what you expect. Is the loading, in this case, applied correctly? So everything now seems fine. So maybe the last thing I'll do, excuse me, if I just turn off the contouring, so clear. So we added in the edge beam that you see there. So let's say PB2, property beam number 2. So that gives me the beam elements along the edge. You see it's been divided up. If I shrink the view, and I need to zoom in quite a lot, but each of these is an element. You can see by selecting it. So each of these is an element that basically coincides with the nodes in the 2D elements. So again, it's all connected. But what I want to do is if I select, well, again, I could select the beam numbers. So I could select the beams. If I get rid of that, if I close the 2D element loading, if I go to Model, Data Modules, Loading, and then Beam Loading, and then choose Beam Loads. So I could then paste So I could then copy and paste in. I'm not sure what it's remembering of the old selection I made. Again, one of these things, it's not entirely obvious why that's happening to me. If I get to the bottom of it, I'll of course update the video description. If I go PB2, so my beam is PB2, and I want to apply a load to the beam. Again, just to make it easier to see. But I want to create another load case. So, just call it. I'm just going to call it beam load, and it's case 8. So we should now see here 8 applied, and you can choose. You can have it as a uniform load going along the entire beam. You can change it to a point load, a linear varying load, and so on. And depending what you choose there, that will open up the options at the end. But I'm just going to say it's a uniform load in the Z direction. and let's say, I don't know, it's minus 20 kilonewtons per meter run. So you remember before, in the very first video, I defined kind of what the units actually are. So if we now display the applied load, so we've got loading diagrams there. If we go to the beam load, so you see it's appeared in the drop down for the cases. Again, it's a load case, not a load, it's an analysis case, so it's existing before the analysis happens, and you can see the beam load that's been applied. If I choose the annotation tool, I can select that, and you can see the value of the load. Again, if you come up to the top, you can change the decimal places that are displayed. So that's put the load on the beam. The only other thing perhaps that I need to add is if I go back to the load combinations, in tasks and cases. So I've added in the beam case, which is number 8. That's not applied to any of this. For simplicity, I'm just going to say that I'll add it into the SLS case, so A8, so analysis case 8, and I'm going to say that it's actually part of the dead load. So I'll add that to there, and again in my dead load combination, I'll add that to there. So I've accounted for the beam load, so we should see that when we look at when we see the results. So I'll close all of this, go back to the floor plate model. I'll turn off the various annotations. Let's make it to the full screen. I'll only show the grid lines, again just for ease. I'll check my restraints so it's all fixed. So then everything now looks ready to go. So I'll save it again. What I'll do is I'll analyze this. So that's just referencing warnings again. It's important to kind of read these and be happy that you understand them. But that looks like it's analyzed okay. If I save the analysis. Again, the very first check I would do is always come to the right-hand side, click on the deformed image button, maybe look at the self-weight case, so the self-weight obviously of the structure. It's showing the applied loading, so I want to turn that off. So I come over to all load diagrams, maybe turn on the shading, and that's broadly what I would expect. So you get the bigger deflections in the span there. You've got the walls obviously restraining that. You've got the edge beam, if I zoom in, attached to the slab, so that shows it is attached. It's not kind of separating from the slab, so the connectivity there seems fine. So that all looks good. So I'm going to stop this video here and then come back and look in a bit more detail at the results and how to interrogate them in a few seconds. So I had considered stopping this video and creating a new one, but really there's not much more to go, so I'll stay with this one. So hopefully everything's been clear so far. So simple. So what do we do now? Well, we've obviously got our model. It's been analyzed. We've now got all the kind of output tools that you see there. So as I said at the start, these are the kind of quick tools to allow you to to display quite quickly the contouring of the various forces and reactions. But equally, you've got the kind of contouring tools here, and also and also these diagramming tools here. So maybe if we just look at this at the diagramming. So we've obviously got all of these cases. Maybe if I look at this at the bending moments. So these essentially are showing the bending moments on the beam elements. So you see we've got bending moments as we would expect in the columns and in the beam on the edge there. And if we cycle through the various load cases, you see they're changing with each one. And equally, we could simply go to the envelope case, which gives us the worst bending moment on the elements. If I want to make it bigger, I can choose the -2 and -2 buttons. So you see there's two lines there, and if I maybe annotate that beam, make it a bit bigger, you see you've got a value of 12 to a value of +12 and -6 and -5 and 9. So essentially these are the minimum and maximum values of the envelope. If we look at the beam, for example, so if I go, and again, apologies, I may be doing this a bit quickly because because of my familiarity with the software. If I come to display and go PB2, so I look at the beam element. If I view that on the side, and then if I increase the actual sort of scale. So this is essentially the envelope of the bending moment diagram. So it's what you would maybe expect to see kind of if you were doing this by hand. So you get the kind of two bending moment plots, one for the minimum and one for the maximum bending moments that you get from the various cases. So again, it's quite a lot of information, but again, it's helpful that it then kind of picks out the maximum bending in hogging and the maximum bending in sagging. And again, you can use the annotation tool to simply pick out what the values actually are. If I come to the actual diagramming options here, you can see that it's already showing that what we've got on the screen just now is the moment in MYY. Now we can obviously change that, but maybe we want a new diagram because often in the columns anyway, we might want to look at the bending in the other direction as well, maybe at the same time. So MZZ, and if we apply that, and maybe to make it clearer, if I go to a top view, if I choose the volume tool that we looked at in the last video, maybe look at the edge column there. So by changing the scale, and it's maybe a bit difficult to see it at the angle I had it, but there you can see we're now seeing the bending in each direction, so the X direction and then the Y direction. And again, you can annotate these. So again, you can obviously look at a diagram in X and then change it to Y, but it might be helpful to show two at the same time, certainly with the stick diagrams that you see there. You can obviously clear that. I can clear that. Apply takes everything off, and click OK. So that basically allows us to look at the bending moments in the stick elements. We can look at the reactions as well. So you could, you could come to the toolbars on the right-hand side. I can click the reaction button, and it will display for the envelope. If I magnify it a bit, it'll display for the envelope the actual reactions. And as before, we're seeing sort of two values to capture the minimum and maximum. So maybe if I go to maybe something that's maybe easier to look at, so it's just one value. So we'll look at the ULS case with all bays with the applied loading. So you see we've got a vertical reaction here of 118. So that's showing obviously all of the reactions. We could come to the diagram, and here, just because we've got all of the reactions showing fx, fy, and fz, it's all selected. Maybe I want to clear that. Perhaps I want to, well, actually I'll cancel it. I'll come out of that, I'll turn off that display. I'll come back to the diagram settings, nodal results, reactions, and I want maybe the vertical reaction, so fz. If I click apply, it's very small. So I could use the times or division to change the scale. You can automatically get GSA to rescale the results by pressing the diagramming button that you see there. And if I do that, it should, I had hoped, have rescaled it, perhaps just because I'm zoomed into too closely. Of course, maybe it's a very small value. If I do ×2 a few times, and I annotate that, again, it's given me the actual value itself. So again, that's one way to look at the results. You can use these diagramming tools. But often one of the maybe the clearer way, or one of the clearer ways I think of looking at it, is to use sort of color blobs. So if we go to the contour settings, we've got pretty much the same type of option. So nodal results, reactions, and the reaction force Fz. And if we click apply, we can see the actual range of reactions. So if I maybe make that a bit bigger. So again, the color blobs, here the size is changing relative to the magnitude, and you can see that obviously the reactions shown there. As you'd expect, there's less loaded in the kind of corner columns compared to the one in the center of the slab. If you wanted just a single size color blob, you could come to contour settings, and constant size on nodes and 1D entities is the option that you would choose. If I click on that and click on apply, then all of the colored blobs essentially are now exactly the same size, irrespective of magnitude. So that can be of use if you get big swings in the actual magnitude, which would then make some of the circles very, very small and others very big. So this gives you a easy way to show the same size of circle, and really then it's just the color that you're looking at in terms of getting the actual value from the sort of contouring bar there. Again, as before, if you choose the select annotation tool on the left hand side and then go over a reaction, again it gives you the actual reaction as well. So again, that gives you the exact figure. That's obviously shown it in blue. If I go maybe to the one that's in red and go over that, again it's showing the text in red. Depending on you could come to the font option at the top, and you can choose, for example, whether it's on the printouts or whether it's just on the screen. You maybe you want black text, so maybe you don't like the colors, which might be well, sensible. Certainly, if there's lots of yellows, that might make it hard to see. If I click apply, you see that's now changed that to black. Personally, I like seeing the text as colors. Again, depending on you can change the font size as well, and again, you can do that for both the print output as well as the screen. If I maybe make this, say, 5, if I click apply, you see it's changed the size of the text. I'm going to maybe put that back to, change that to 3. It's maybe a bit small. And really, it's a case, I think, of just experimenting and seeing what sort of size you're happy with. So if I go back to the contouring options, I want to get rid of that. So if I hit clear and apply. So what else? Well, that's the basic way of interrogating the model. I mentioned, I think in the very first video, in the kind of 2D element results, you've got projected and derived values. Projected is simply projected onto the surface that you're looking at, and derived are things like principal stresses, principal forces, principal moments. So you can again experiment with all of this in your own time. If I look at projected moments, I suppose, as I mentioned in the first video, the ones I think that we should be looking at are the mx plus mxy, or the my plus mxy. So essentially accounting for the torsion as well as the bending effect. So as a wood armor type of interrogation of stresses. So we would maybe go to that. We would choose apply, and let's look down from above. So this is showing the bending moments in the slab. Again, in GSA, the sign convention, it's in the help manual, but MX is essentially bending in the X direction. MY is bending in the Y direction. So we've got obviously here the bending moments. If I were to maybe just look at the imposed loading, so this is the imposed loading case in the X strip 1, the X strip 2. So this is with imposed loading. Actually, it's maybe going to be easier if I create a new view. So again, one of the real kind of good things about GSA is that there's a lot of display options. So here I've got obviously my kind of view of the model, and here we've got these contour plan. So I can, at the same time I go through my contour plans, I can have this view to the side to remind me what the loading actually is, and of course making me think, well, does the loading actually make sense? I suppose here the other thing is you're obviously kind of seeing each element with a single color. If you wanted to, you could come back to the contour settings, and it's remembered that that's what you're looking at in this view, and you could average the values at the nodes. If you hit apply, essentially it smooths off the actual contouring. Again, it's really up to you. I personally don't really do that. In a way, I like to see the step changes between elements, but I'll leave it on for just now. So cycling through, we've got strips 1 and 3. If we look at that, so essentially there's no loading or no imposed loading on this middle strip there, and that's broadly what you're seeing with the contouring. Actually, so I mentioned in the first video, if you hold down Control Alt and L, that toggles how the legend appears. So I've now excluded the legend area from the model area. So as we would expect, we've got more bending in the X strips. So in the Y strips, where you do see the applied load, and not so much here, because there's nothing really kind of being applied there. So the bending there is very much caused by the loading on each side. And again, we can just go through our model. We can look at the effect of the applied loading. So there we've got the loading on this middle strip. As you would expect, we've got the bending moments that occur there, and not much happening on either side. So again, it's one of those visual checks that we do to check, does the bending moment that we're seeing correspond to the applied loading? And again, there's no real calculations involved at this stage. It's just, is what we're seeing what we expect? Again, one of the fundamental checks that we need to carry out. So that's obviously MXY. You can do exactly the same thing, obviously, for MY as well. And I'm not going to go through that. It's exactly the same thing. I'll clear that. The only other point or the other thing I'll draw your attention to or two things with the 2D elements. If in the derived forces and moments, you can look at the through thickness shear. So that's just telling me it's going to change the contouring. If I go apply, so that's then telling me the shear going through the slab. So that's what we would use if we were checking punching. And again, the help menu describes kind of what how this is actually calculated. If I did go back, sorry, just to this bending to display again. So this is MX and MXY. So the thing I would usually do is I would go to specify my contour values, and I might set the extreme value to 0, and then apply. So what that means is it then allows me to say, well, I'm only going to look at sagging here. So again, sagging, tension at the bottom of the slab is a negative value in terms of the GSA sign convention. Conversely, I could delete that, put it as the first contour, click OK, hit apply, and now what we're seeing is the areas which are in hogging. So again, it's an easy way, and I think a much easier way to view a results output if you're only looking at hogging or sagging. As I mentioned again in the first video, if we wanted to kind of retain this, we could right-click, we could save the graphic view, and then give it a name. So that then means that each time we restart a particular model, we've always got that view defined, so we don't have to keep redefining the actual contouring itself. In terms of redefining the contouring, the other thing that I would typically do is that if I know my section thickness, I can work out what the resistance is, and then I can put in the actual resistance values. And by doing that, it then allows me to see how much reinforcement I need, or if I've got a slab, I might have B16s at 150 as a standard mesh. Then anything above that I want to see contoured, because that then tells me where I want additional reinforcement. Again, if this isn't kind of clear to you, again, please get in touch with me and I can explain it in a bit more detail. I suppose the point is we can use the contouring to help us understand where we need reinforcement. Yes, there is a design module in GSA that's covered in the tutorial that's installed with GSA. I'm not going to go into that, but there's no real need to use that. It's perhaps more instructive to put in the values yourself here. So the last thing I'm maybe going to touch on in terms of the results, if I clear that. So obviously we're doing an elastic analysis, and as with all software, we've seen the deflected shape before. I'll just turn off the annotation of the restraints so things are clearer. I'll make this full screen again. If we come back to contour settings, global results, 2D element results, I should say, 2D displacements, we can obviously show the actual displacements on the slab, which is what you can see there. Maybe if I look at the self-weight case. So as you would expect, I mean, that looks in terms of a sort of a qualitative assessment, that looks like what I would expect. There's a big deflection in the middle of this bay around the penetration. Again, deflections in the bay here. And again, you've got the stiffening effect of the core. We're reducing the deflections in the bays immediately adjacent to it. But you do notice that all of these deflections are really small. And of course, that's because this is just an elastic analysis, and it's not taking into account cracking at all. So that's something that you would need to consider in terms of using this. So you can't take these values as they stand, from this model anyway, and use these to look at whether the deflections of your slab are fine. So how might you address that? Well, I'm not going to go into it in this video just because it's getting a bit long, but I'll touch on it on the next video when I look at changing some of the element properties to maybe look at accounting for things like creep and possibly cracking. So I hope this has been useful. Again, experiment with the software, and I'm always happy to answer questions if you do want to use GSA. Thank you.